This is 4.2, number 95. There's some concepts here that you really want to pick up because it's weird. First thing to notice, this is the derivative of f. Not f, it's the derivative. So the first question they're asking, where is it increasing and decreasing? This is called graphical analysis. You take a graph and you analyze it and you pull out some incredible information out that you would have never dreamed possible a moment ago. So you should know a function is increasing if its derivative is positive, a function is decreasing if its derivative is negative. If you don't know that, you're in trouble for a quiz coming up soon. In fact, that was on your last quiz last Friday too. It has to be part of your common knowledge. Okay, so when is the derivative positive? When is it negative? I claim the derivative is positive when it's below the x-axis. So in this region, f prime is negative. And I claim on all this region, I claim f prime is positive. Now some might say, no, it's zero right there. It is zero there. We'll deal with that. So based on that, I'm not going to write this all out. Just follow along. I should write it out. I would say f is increasing on what interval? I would say from -2 to 2. And then I would give a reason because, I'll write it, it's going to disappear. F prime is positive on -2 to 2. So that's my justification for where it's increasing. Now, some might say, no, but the derivative is zero there. You can't say that. If you're not comfortable with that, you could say -2 to 0 and 0 to 2 and break it up into 0 to 2. Break it up into two separate ones. And you'd be fine making two regions, here to here and here to here. The reason I'm okay with 1, because it's increasing from -2 to 0. So I'll have it increasing. At 2, it's flat, right? I mean, at 0, the derivative is 0, so the tangent line is 0. But then it starts going up again because it's increasing here. So at that point, even though it's flat, if it's increasing to the left and it's increasing to the right, it's also increasing through that 0 tangent line point. So I can have it all as 1 if I want to. Then for decreasing region, I would say it's decreasing on the interval from -3 to -2. It's on this region. Why? My justification would be because the derivative is negative on that interval because it's below the x-axis. So it's pretty cool that just from that picture, you're able to find the regions of increasing and decreasing. You didn't have to take the derivative. You didn't have to test points in each region. You just look at the graph and it's like, wow, that's pretty easy. I like that. And so let's just keep going here. There's more information. Now they want critical points. So let me erase all of this. Critical points. Critical points are points where the derivative is 0 or does not exist. If you look, there's no holes or gaps. That's not what I wanted. There are no holes or gaps anywhere here. This derivative exists everywhere. There's nowhere where it doesn't exist. But there are two places where the derivative is 0. Right there and right there. So where are the critical points? For the critical points, you would say at x equals -2 and 0. So you'd write that out. F has critical points at -2 and 0. Next, they want to know if they're local max or local min. Well, look at the derivative. This red is the derivative. So therefore, the derivative is negative there. It's positive there. What happens at -2? There's a relative minimum. The justification for relative minimum is when the derivative changes from negative to positive. So you would say there's a rel min at x equals -2, and your justification is because f prime does what? Changes from negative to positive at x equals -2. So that would be your justification at this point. You write that out. Now, if you look at this critical point, you will notice it's positive to the left, positive to the right. So does it have a rel max or min? The answer is no. Why? It doesn't, because it didn't change signs. So you would say it has neither at x equals 0 because the derivative doesn't change signs there. Okay? Now, I'm going to switch C and D. I'm going to do D first and then C. This is the part you really need to listen to. I have 3 minutes. I need to get this out because this is the crazy part. It's kind of cool once you get it, but it takes a while for people to get this. I claim from here to here, f prime is increasing. And I claim from here to here, f prime is increasing. And then I claim from here to here, f prime is decreasing. Here is the kicker. Listen very carefully. This is like the big takeaway. You learn if any function is increasing, its derivative is positive, right? That should be part of your brain. If it's not, you're behind and you're in big trouble. If f is increasing, then its derivative is positive. If f prime is increasing, then its derivative must be positive. What's the derivative of f prime? That means f double prime must be positive. That's the big takeaway. If f prime is increasing, its derivative, f double prime, must be positive. Increasing, decreasing functions. So here, f prime's increasing. Its derivative must be positive. So the derivative of f prime must be positive. F double prime is positive. Here, f is decreasing. If any function is decreasing, its derivative is negative. Therefore, its derivative, f double prime, is negative. Okay, so I don't have time to write this all out, but we know f is concave up from -2 to -1, and f is concave up from 0 to 2. Why? Because the second derivative is positive on those regions. Craziness. We found that from the graph of f prime. Then we would say f is concave down from -1 to 0. Why? Because we found the second derivative is negative on that region. And then the final kicker, we have inflection points at -1, and inflection point at 0. Why? Because the second derivative changed from positive to negative or negative to positive at those points. The second derivative changes signs at those points. It's a lot of stuff I threw out at you right there. If you didn't get it now, I highly recommend you watch this video again and just get it, because it's a very common question on the AP test. Okay?